Hey there, folks. This is Mr. Young. I'm going to take you through some notes on polar and nonpolar molecules. And before we talk about polar and nonpolar molecules, just have to do a little recap of something you should know from earlier in the year. Ionic compounds versus covalent compounds. Just a reminder, ionic compounds are formed between a metal and a nonmetal. They involve a transfer of electrons. The metal loses some electrons, the nonmetal gains some electrons, they become a positive and negative ions, and that's a transfer of electrons, and they stick together because opposites attract. Covalent compounds involve only nonmetals, and covalent compounds involve a sharing of electrons. Covalent starts with a C, caring starts with a C, and it rhymes with sharing. Okay, now, what does polar mean? You have heard that the Earth has a magnetic field. The Earth has a North Pole and a South Pole. The Earth is different on each end. The North Pole and South Pole are different from each other, okay? And that means the Earth is polar. Something that's polar is different on each end. If we look at these two molecules, one is Br2, one is HBr. Last week we learned about electronegativity. Electronegativity means how strongly something attracts electrons. So these two bromines, they're the same element, so they share their electrons equally. They have the same electronegativity. But in HBr, bromine has a stronger electronegativity, hydrogen has a weaker electronegativity. So in this bond, bromine is pulling the electrons more closely towards itself. This HBr molecule is different on either end, whereas this Br2 molecule is the same on either end. You could also just look at the electrons. This Br2 molecule has extra electrons on either end. It's the same on either end. The HBr molecule has extra electrons on one end, but not on the other end. So we would say that the Br2 is nonpolar. There is equal electron distribution, equal electron sharing. HBr is polar. It is lopsided. It has unequal electron sharing. And in fact, there are a lot more electrons over here on one end. So it's polar. Polar means lopsided. Okay, going through the notes. So polar molecules are molecules that are lopsided in terms of their electron distribution. We could also say they are asymmetric. You may have learned about symmetry in art class, right? Polar molecules have a positive end and a negative end. Okay, so if we look at all these three molecules, you can just often look at the diagram of the molecule, the Lewis structure, and if you see some extra electrons at one end or at one side of the molecule, not at the other, that means it's a polar molecule. Now we can also talk about lines of symmetry. Okay, polar molecules will have one line of symmetry or maybe sometimes no lines of symmetry. Now what's a line of symmetry? Okay, here we go. On page 2 of the notes, imagine you have a heart drawn on paper and you want to fold the paper so that you have two halves of the heart that are identical to each other. Well, there's only one way to do that. If you fold it horizontally, the two halves of the paper will now have identical parts of the heart on it. If you have a shape like this letter H, you could fold it horizontally. You could fold it vertically, and each way you'll get the same thing on either side of the fold. So the heart has one line of symmetry. The H shape has two lines of symmetry. Okay. If something has one line of symmetry, you can only fold it one way to have identical halves. All right, back to this. So if we look at these molecules, we could fold this one along the middle and we would get the same thing on either side. Now, don't look at the shape of the letters. You're looking at the fact that, okay, this is half a carbon atom on this side, 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 half an oxygen, half a hydrogen, half a hydrogen. We're not talking about the shapes of the letters, but we're talking about the actual atoms that are in the molecule. Okay, this CH3Br, you could fold it this way. There's no other way to fold it. If you try to fold it vertically, you'd end up with a bromine on one half and a hydrogen on the other half. That would not be symmetrical. And then this H2O, you can fold it this way. You will just get one line of symmetry. There's no other way to fold it. Anything with one line of symmetry will be a polar molecule, okay? Or it might have no lines of symmetry if it's a really weird molecule. Now I'm going to also add one more molecule here, HBr. Remember, we said it is a polar molecule. With all these molecules, you can either look at them and see that there are electrons more on one side of the molecule, or you can try the symmetry trick to figure out if it's polar. Polar molecules are lopsided in terms of their electrons, and polar molecules have one line of symmetry. One more good one to add would be NH3 ammonia. That's a very common example of a polar molecule. Okay? It has these electrons at one end, and it also has one line of symmetry. Moving on, nonpolar molecules are symmetric in terms of their electron distribution. They do not have a positive end or a negative end. So if we look at CO2, CCl4, and C5H12, these all have two or more lines of symmetry, and they also have even distribution of the electrons. Yes, the CO2 has electrons over here and electrons over here. They're evenly distributed. Same with the CCl4. There are lots of electrons, but they're evenly distributed. And then this long chain carbon molecule, we'll learn more about these next week. This has, you can't see any electrons in the diagram except for the two electrons that are in each bond. They're evenly distributed. And with each of these molecules, you can fold it in at least two ways. With something like CCl4, 4 different ways you can fold it to get the same thing on each side. CO2, 2 different ways you can fold it. 2 lines of symmetry means it's non-polar, means it has an even distribution of electrons. Another good one to add would be Br2 or O2 or N2 or H2. Any molecule that's made of 2 identical atoms will have 2 lines of symmetry and will be a non-polar molecule. All right, why do we care? Well, polar and nonpolar molecules do not like each other. They do not mix, they do not dissolve in each other. We say they are immiscible, they do not dissolve, like oil and water. Water is a polar molecule. Oil and water do not mix, they do not dissolve in each other, so oil must be a nonpolar molecule. In fact, oil molecules have a structure that's very similar to that long chain of carbons that we just saw on the previous slide. The rule for this is like dissolves like. Polar things will dissolve in polar things, so water and ammonia will dissolve in each other, but water and oil will not mix or dissolve in each other. Now, everything up till now I've been talking about is about covalent compounds. We're talking about compounds mainly made of nonmetals. But ionic compounds do come into this conversation. Na will give away an electron. Cl will steal an electron. That means Na will form an Na plus and Cl will form a Cl minus. Those are 2 ions that will stick together. That makes an ionic compound. Since you've got a very positive thing attached to a very negative thing, ionic compounds are basically the extreme example of polar substances. They are very, very polar. They will easily mix or dissolve in polar substances. The molecules that we've been talking about above, they're molecules that have a partial positive charge at one end and a partial negative charge at the other end. But ionic compounds actually literally have a positive thing and a negative thing that are stuck together. Okay, so they will hang out with polar molecules, not nonpolar molecules. That's why salt, NaCl, dissolves in water, but you can't get salt to dissolve in oil. Okay? All right, here are some molecules, and you're going to just try to figure out their lines of symmetry. Hit pause, try to figure out how many lines of symmetry and whether it's polar or nonpolar. Okay, we're back. Here we go. 1 line of symmetry, 4 lines of symmetry in this case, 2 lines of symmetry, and this last one is similar to ammonia, NH3. It's got 1 line of symmetry. That means these 2 with 1 line of symmetry are polar. These ones with 2 or more lines of symmetry are nonpolar. So when we're trying to figure out polarity, we look at the whole molecule, either looking at how the electrons are distributed overall or what kind of symmetry it has. This one in the middle, it's got the electrons evenly distributed and it's got 2 or more lines of symmetry. It's a nonpolar molecule. This one here has electrons at one end, not at the other end. It's got 1 line of symmetry. It's a polar molecule. This O2 has 2 lines of symmetry. It's got electrons equally at either end of the molecule, so it's a nonpolar molecule. All right, going to go through some example problems using that idea of like dissolves like. All right, we've got water, that's a polar molecule, and oil has a very similar structure to this long chain of carbons. This is a hydrocarbon. Again, we'll learn more about those next week. Will this substance below dissolve in oil or dissolve in water? Remember, like dissolves like. Okay. Well, this CBr4 has equal distribution of electrons. It's a nonpolar substance. It's going to dissolve in nonpolar substances. Remember, like dissolves like. What about this one? We've got C4H10, and then this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's C10H22. Well, like I said, long chain hydrocarbons are always going to be nonpolar. Okay, carbon chains are nonpolar. You could fold it horizontally, you could fold it vertically, you get the same thing on both sides. So they like dissolves like. Will this substance below dissolve best in oil or water? Remember, water is polar. It has a negative end and a positive end. Oil is nonpolar. It doesn't really have a negative end or a positive end. So you've got KBr, an ionic compound made of positive ions attached to negative ions. Will it be more attracted to water or more attracted to oil? More attracted to water, because water molecules have a negative end. This little delta minus and delta plus means it's partly negative here, partly positive here. Remember, in the notes previously, I said ionic compounds love polar things because the positive K plus can attach to this negative end of the water molecule, and the negative Br minus can attach to the positive end of the water molecule. Okay, we've got NH3 ammonia. Will it dissolve in oil or water? Well, it's a polar substance. It will dissolve in a polar substance like water. What about this one? We got CaCl2, calcium chloride. So it's made of 2 chloride ions and a calcium ion. Will it dissolve in oil or water? It's an ionic compound. It loves polar. Ionic compounds love polar because they're the extreme example of something that's polar. Okay, we got oxygen. Oxygen does dissolve in water. If it didn't, fish wouldn't be able to breathe underwater. But will it dissolve better in water or in oil? Turns out it'll dissolve better in water because it actually, better in oil because it actually is a nonpolar substance. Yes, it will dissolve in water. It's a little bit of a gray area. Water is definitely unique. That is going to bring us to the end of these example slides, I think. Yeah, that brings us to the end. Thank you for watching, and catch up with you later.